So now I will go to my talk. Okay, here it is. Hope you can hear my slides. Okay.
You can see them.
Thanks. Okay, so as Laurent was mentioning, I'm going to talk to you today about the bi-objective long-haul transportation problem on a road network. This is a joint problem with Ola Jabali from the Politecnico di Milano, Andrea Moro and Grazia Speranza from the University of Brescia, the former institution where I used to be, and Alberto Simonetto, who is not from academia. He instead works in a company, Multi-Protection, which inspired our work. Indeed, this work is coming from a joint project with this company. So, okay, so the main topic of my talk today. Okay, let me first introduce the following. My research work, as Laurent was saying, is mainly based on optimization. So working on problems that comes from real application or closely related to real applications, optimization problems, and devising solution algorithms for their solution, either exact or heuristic. What I'm going to present you today, has the same origin. We are still talking about an optimization problem, and still we want to devise an optimization algorithm for solving this problem. However, in this case, the main focus was not the optimization in itself, but instead the issues, let's say the practical issues that we had to face. Based on the fact that given that this work was a collaboration with this company, we wanted to devise a tool which was useful in practice so that they could use in their specific applications. So, and as I will present you in a moment, we had to face a number of practical issues, and so we in practice we adapted our methodology to be able to face these practical issues that I will present you. Okay, so this is the outline of my talk. I will first present you the project from which this research work has started, the project that we had with the company and that is still going on today. And then I will formally describe the problem, how we modeled it, and I will spend some time in describing what were the challenges that related to the practical application of this problem. I will not spend too much on the literature review, but I will briefly present you the links with the former literature dealing with some aspects related to the problem we are dealing with. Then I will present you the algorithm, the methodology that we have devised for solving the problem, and then some simulations with results and conclusion. Okay. Starting from the motivation, as I was mentioning earlier, the company we collaborated with is Multi-Protection. This company offers security service devices for carrier and transportation companies. So in practice, they develop and install on trucks both the hardware and the software for security services. So they have equipment which keep track of the trucks when they are traveling. So they have well, it's a rather standard equipment. This one, GPS and all these tools that gives online information about speed, fuel consumption, driving times, etc. And also, in addition, they have the equipment detecting whether the truck is going to be attacked. And so in this case, these equipment send alarms for preventing those kind of attacks. So this is the main business of this company. And the collaboration with this company started from the fact that the manager of the company at some point realized that the equipment that they have on the trucks they are serving provide them with a lot of information, and they were just partially exploiting this information just for, let's say, the security service objective. However, he had the idea of developing some additional tools, some additional services to sell to the company customers. The additional services exploiting this information. And the first idea he had was, okay, why not providing a tool that tells to the company, the customer of the clients of this company are, as I was mentioning, transportation companies, and that typically make long-haul transportation, so transportation on long distances. So the idea of the manager of the company was offering a tool that was capable of telling to the customer what is the best path or the best trip for going from a point to another point. So these transportation services are typically made of an origin location where you have to pick up some goods and the destination where these goods have to be delivered. So the idea was, okay, let's provide to the company a tool that tells them what is the best way for going to from the origin to the destination. This seems to be quite an easy question, right? Because we have a lot of navigators that tells us exactly this. So we query them, we say, okay, I want to go from here to here, tell me what is the best way to go to destination. But this is not completely true when applied to this specific context. Okay, so first of all, we are talking about long distances. And one of the major components of the transportation cost when traveling these long distances is the fuel cost. And of course, companies want to minimize this fuel cost. And if you think about that, okay, a navigator tells you what is the best, let's say the shortest of the fastest path from going from the origin to the destination, but it doesn't tell you where you have to refuel. And this is a critical decision because the fuel prices has a lot of variability according to the place in which you are going to make refueling. Especially on long-haul transportation, where you have paths that traverse different countries, and the fuel price varies from country to countries. But even within the same countries, for example, in Italy, we know that if you refuel on highway, you're going to pay much more than refueling out of the highway. And so maybe with a short detour on the path, by exiting just for a few kilometers out of the path and refueling out of the highway, you're going to save a lot of money, especially if you think about trucks which have a 500 liters tank. So this is a critical decision that is not taken into account in the navigators that are available, and it's important for the transportation company. And indeed, the manager of multi-protection, when talking to their clients, he realized that they have these issues. On the other, and also a second point is that still the navigators they do not include, I mean, the constraints related to the drivers that have to drive these long distances. So drivers have to be compliant with what is called hours of service regulations, that are regulations imposed for us at the European level, that impose to have breaks or rest after some given hours of driving to guarantee the safety of the drivers and of the other drivers in the roads. And again, the standard navigator, when you're going to plan the path between 2 points, that doesn't tell you where it is convenient to you to make a rest. So there are these two issues which are currently not faced by standard navigators, and the manager of the company wanted to devise a tool taking into account these two features. And so we had this lengthy discussion, and at the end we were able to define, let's say, formally the problem. That is the one I'm presenting you here, the long-haul transportation problem. That is the problem in which you have an origin and destination, and you want to find the best path for going, or the best paths, because there can be multiple paths going that are, let's say, Pareto optimum, going from the origin on destination, and there can be multiple paths because we are considering two objectives. Indeed, as the title of my talk, we have a B objective problem, because we want to minimize the duration of the path, because according to the duration, we associated with the duration, there is the cost component that is linked to the driver's wage. So the longer the duration, the longer is the cost that you have to pay the driver that is driving the path. And also we want to minimize the fuel cost. Okay, so we have to decide what is the path and where we want to stop for refueling. And the path has to satisfy the constraints related to the hours of service regulation for the drivers, and also we need to be sure that we will not run out of fuel. So it has to be feasible according to these two set of constraints. Okay, so this is the problem that we faced, and for which I will present you now the study and the algorithm we have devised for doing that. But before presenting the algorithm, let me investigate a little bit more on the challenges associated with this problem. So briefly, first, the hours service regulations. As I was mentioning, these are regulations imposed at the European level for the safety of the drivers. This is a summary of the main regulations for the European regulation. There are three main rules. The first one is about the continuous driving hours. So a driver cannot drive for more than 4.5 hours consecutively. After that, he or she has to make a break of at least 45 minutes. Then there is the daily driving rule. That is, in a 24-hour period, the driver cannot drive for more than 9 hours, and then it has to make a daily rest of at least 11 hours. And then the weekly driving rule, that is, in a week, a driver cannot drive for more than 56 hours, and after that it has to make a rest of at least 45 hours. So these are the three main rules that we need to take into account in order to build the path. And then this slide is just to introduce the practical impact of the study we are making. So this slide comes directly from the company. So when the company started to think about this problem, they also submitted a project which got financed by an institution. And this picture that you see in the slide comes from this project, from what they submitted to this financing institution. So in this picture, you have two paths that goes from Rome to London. Path A is the standard one. So if you go to a navigator and you ask the path, what is the best way for going from Rome to London, the output is typically path A. Path A starts from Italy, then goes to Switzerland, France, and then London. This is the shortest path, which is around 4,050 kilometers long. And the refueling cost, the calculated refueling cost along this path is 2,262 euros, more or less. And what they did was, analyzing an alternative path, which is path B in the picture, which instead of going from Switzerland and France, it goes from Switzerland, Germany, Belgium, and United Kingdom. And on this path, what is important is that in Belgium, typically, the fuel cost is much lower than in France or in the nearby countries. And indeed, this path is slightly longer than the former, so 4,172 kilometers, but the fuel cost is much, much less. So it's less than 1,180 euros. So we're going to save a lot by traveling this slightly longer path. And so this was their initial motivation for studying the problem. So starting from this example, okay, we started the study of the problem, and the first thing that we did was, okay, we want to devise a tool that works on the road network, right? Because I mean, given that this has to be implemented in the company's framework, we have to interact with the road network. And then one of the main decisions that we have to make in this problem is, where do we want to stop to make refueling? So what is the best path from going from origin to destination? And along this path, where do we want to rest and where do we want to stop for refueling? Okay, and given that the refueling cost is highly variable from country to country, but also from refueling station to refueling station, the idea was, okay, let's study alternative path from going to origin to destination, and then studying individually each of these paths to see where we should stop for making either rest or refueling. Okay, in this slide you see 3 paths that goes from Rome to Stuttgart, the red, purple, and orange path. And so we then analyzed each of them individually. Then, by focusing just for a moment on the refueling decision, if we want to decide where to refuel, it means that we have to consider all the potential refueling stations that are at least fairly close to this path. So we considered an area, a circle of 500 kilometers radius along each of these paths, and then we counted all the potential or the possible refueling station where we could stop, in order to have an idea of the alternative solutions that we have in order to determine what is the best path. Okay, by considering just the 5 kilometers area around this path, we found more than 1,000 refueling stations. So we immediately got aware of the fact that in a practical setting, especially when considering the fact that we are dealing with long-haul transportation, the size of the problem is huge, because the number of alternative solutions or the number of alternative places where we could stop is extremely high. And this was a big issue that we needed to face in order to devise a solution algorithm that is useful in practice, so is capable of handling this huge dimension of the problem. This is coupled with the fact that, okay, we are dealing with long-haul transportation. Indeed, not only the company itself, the clients of the company are typically in this business, but also we found a recent study by the European Commission that shows that in Europe, the average distance traveled for road freight transportation is between 300 and 1,000 kilometers. So the business is like this. So we have a lot of companies performing this long-haul transportation. So the longer is the distance, the more are the possibilities of where you could stop for refueling, and so the larger is the size of the problem. So we had huge dimension, and this was a main challenge in shaping the algorithm that we at the end devised for the solution of the problem. Okay, so now, before presenting the solution algorithm, let me talk briefly about literature review. So what we found in the literature that is related to our problem. So we focus mainly on three, let's say, classes of contributions. The first one was contributions studying transportation or routing problems on road networks. There is quite a good literature there. The papers I am citing in the slide is recent survey that is revising the literature on the topic, and that appeared recently in Networks in 2018. And then I'm going back then to present you some of the features of the contribution dealing in, with this problem, with routing problems or road network. I'm coming back in a couple of slides. And then the other two main features of our problem are related to our service regulations, that they have an impact on the duration of the path, and so on the cost related to the duration of the path itself. So in this topic, there is also quite a good literature. The two papers I'm citing here are the first ones dealing with our service regulation. The first one deals with US regulations, and the second with Australian regulations. But then after these two papers, there has been quite a few others dealing with the problem of building routes for road transportation that are compliant with our service regulation. And then the last class of the literature is related to problems that still transportation problems in which the refueling decision is considered. So in which one of the decisions is where the drivers should stop to make refueling. For this last class of problem, there are much fewer contributions, so meaning that this decision, this is quite surprising because refueling is one of the major components in transportation, but there are not that many contributions taking into account explicitly the decision of where refueling should take place. And in addition, we couldn't find any contribution in the literature dealing at the same time with hours of service regulation, refueling, and working on road network. So the majority of the literature doesn't take into, as I was mentioning, does not take into account refueling decision, and they just assume that the fuel cost is proportional to the distance. And as I was mentioning, this is not true. This might be considered as true just for short distance transportation, where you don't have to refuel during the trip. You just refuel before starting, and then before starting, you might decide where to refuel, but this is not a decision that you have to take into account when optimizing the route. But you don't have to refuel when you are traveling your route. So in this case, it is reasonable to assume that the fuel cost is proportional to the distance, but not in long-haul transportation. So this is important to take into account, and this here in the slide you see again some data that provides motivation for taking into account the decision. In 2019, the diesel price in Italy was 70% higher than in Germany, and even in a more restricted area, we accessed the diesel price in the area of Milan on the 12th of June 2020, and it varied between 1.15 to more than 1.8 euros per liter. So there is a high variability even in a restricted area. So the decision about where to refuel is indeed important. And then going back to the issue related with road networks, and just to present you briefly a story, let's say history of how these transportation or routing problems have been represented in the scientific literature in the past years. The standard convention for representing routing problem used to be, okay, you have your points that you need to serve, and you represent them as vertices of a graph, and then the arcs of the graph are links between pair of points representing the best path that for going from the first to the second point. Okay, this has been the standard convention, and it is still used as a convention for representing routing and transportation problem. But then one first issue raises, okay, when you say that the arc represents the best path that joins the 2 points, what is the best path? Is it the shortest? Is it the fastest? You might be interested in having both shortest and fastest. So in this case, if they are not the same, typically in practice, they are not the same, the shortest is not the fastest, which one do you choose? So there is this first issue that was studied and solved by considering multigraph. So in multigraphs, you still are the vertices representing the locations that you have to visit. And then each pair of location might be linked through multiple edges or arcs that are Pareto optimal path according to the attributes that you are considering. So distance and time, for example. For example, here you have vertices 0 and 4, and you have, if we are close to each edge, we have the 2 attributes linked to the edge. Let's assume that the first is the distance and the second is the time. Then you have both the shortest and the fastest path linking 0 and 4. So you have these 2 paths. But the more are the attributes, the more are the Pareto optimal paths that can link to vertices. So when moving to this representation, you still face a first issue related to the fact that you might have a lot of arcs linking any pair of vertices. But then the more recent literature started to propose graphs that instead provides a representation of road networks. Okay, here is an example of a graph that simulates a small piece of a road network. Still, in red, you have in black, you have locations that you need to service, our vertices 0, 2, and 4. But then you have also additional vertices in white that are not locations that you need to service, but represent features of the road network. Specifically, in this case, they are intersections. And intersections between roads and streets in the road networks. And so you see that the size of the graph in terms of number of vertices of the graph increases, and then you have also an increased number of edges linking any pair of vertices with their corresponding features. And if you think about this translation, I mean, this representation of road networks into a graph, where on top of having your location that you need to serve, you have also the additional vertices that represent the topology of the road network, you immediately see that the size of the corresponding graph increases very fast. For example, here you have on the left part of a road network and the corresponding graph representation on the right. So we have the 2 locations A and B that are 2 that we want to visit, but you see the number of vertices and edges that represent the road network topology is much larger than the 2 standard points that we would have included in the very first convention used in the representation of routing problems. And this is just another slide for showing you that the size of the graph increases very fast. Also, there is another issue. Even if we are capable of dealing with the dimension of this increased graph, there are still features that or information provided in the road network that are difficult to be represented in the graph, like obstacles on the street or traffic light or roundabout, etc. So this is to say that the graph representation of the road network is not always ideal. First, because it might have huge dimensions. Second, because it is not capable of capturing all the information that you have when dealing directly with the road network. So our choice, as the choice of some contributions in the recent literature, was to work directly on the road network. Okay, so we didn't we didn't went through the representation of the network on a graph because of dimensions and because of not losing important information. And now let's go to the solution algorithm. Okay, what was the main idea behind the algorithm that we devised? Oh, okay, given the issue associated with the huge dimension of the problem, our idea was, okay, let's build the path or the path that goes. So we have our origin destination pair. Okay, we start from the origin and we dynamically build and construct partial paths that goes from the origin to the destination. So we analyze multiple partial paths that goes to the destination, feasible paths, and we construct all of them dynamically. So we move forward up to the point in which we need to stop because we are running out of fuel or we are running out of time. And then so we have a first portion of the path that goes to destination. And then from that point, we continue in building the path for another leg of the path, still feasible, up to the point we have to stop again, and so on, up to the point in which we reach the destination. So we dynamically build these partial paths, which are, let's say, legs of the complete path. And we build multiple paths, and then we analyze all of them, and we just keep the best ones, so the Pareto optimal ones, and discarding the dominated ones. Okay, so we started from, okay, I will present you step by step how the algorithm works. So we have our origin destination pair. So the first thing that we do is, okay, let's determine the k best path that goes from the origin to the destination. In our simulations, k has been set equal to 3. So we built this path from origin to destination by simply doing the querying on the navigator. That gives you the 3 best path. But of course, this path might be infeasible because the navigator doesn't take into account nor refueling nor driving rules. So then, second step, we analyze each of the 3 paths individually. So we take one, for example, the black one in the picture, and we analyze this path in order to see whether, according to the remaining driving hours and the tank level that we had when we started from the origin, this path can be feasibly traversed up to the destination. If the answer is yes, okay, let's stop. This is a path, and we don't do anything else along the path. But if this is not, it means that when traversing the path, at some point in the middle of the path, we are running out of fuel or driving time. So it means we have to stop. And then we devise the procedure that I will explain you more detail in a moment to find stop location. So when we need to stop, so shortly before we are running out, either running out of fuel or running out of time, we call this procedure to determine the stop locations, either rest locations if we're running out of time, or refueling stations if we're running out of fuel. Once we have found the, and we try to determine multiple locations because there are multiple alternatives. For example, if we have to stop for refueling, there might be multiple refueling stations close to the place in which we have to stop, and we want to consider all of them in order to devise what is the best choice, to determine what is the best choice. For example, here we have determined 2 stop locations, And then we build two partial paths that goes from the origin to each of the two stop location. And note that these two partial paths, starting from the origin and going to the two locations, are not feasible because we stop before running out of fuel all the time. So we have two partial paths from the origin to the stop location, and then from each of the two stop location, we repeat the procedure that we had before. That is, we build, or we determine again the free best path that goes from each of the two locations to the destination. Okay, so as summarizing from our initial infeasible path, we have at the end two partial paths to the stop location and another 6 partial paths that we still have to analyze to see whether they are feasible or not, that goes from each of these locations up to the destination. Okay, and so you see the number of paths easily and fastly grows when we move from the origin to the destination. Each of these paths, we use a data structure to keep track of all the paths that we built, or the partial path that we built. So we organize them in a tree rooted at the origin, where the leaf of the tree are all the destination points, and each path going from the origin from the root of the tree to the leaf is an origin destination path. And each path from the root to a node which is not the destination is a partial path which is feasible, and the only potential leg or arc of the tree which is infeasible is the one that links a node to the leaf, that is to the destination, one of these partial paths over here. Okay, so this is just what I was mentioning you now. Okay, this is the scheme of the algorithm. I've already shown you how the branch to destination procedure works. This is just the procedure that determines the k-best path from the point that we are considering up to the destination. Then we are going to select and analyze an arc which is infeasible, so that cannot be traversed up to destination, because then we analyze this path in order to determine where we need to stop. And I'm presenting you now how we determine, how we find the stop location. And then we also use the combined stops types procedure for combining different type of stops. I will also present you in this in a moment. Okay, so as I was mentioning, these two procedures I presented you in the former slide. So let's now focus on how we determined where to stop. So when do we need to stop? There are two reasons why we need to stop: because we are running out of fuel. And in this case, our rule is starting to search for refueling stop when search for refueling stop when the tank level is between 10% and 5% of the maximum level. Or we might stop it because we are running out of time. And in this case, we started to look for a rest location from the point in which we have 5% of the driving time remaining backward. Okay, so we can have 3 different cases according to the two reasons why we stop. Either the reason why we're stopping is running out of fuel, and so we will have the first case over here, where this beta tau and gamma tau are the two locations associated with 10% and 5% of the tank level, the two locations on the path that we are traversing. So it means that we will look for a refueling station on the segment of the path that goes between these two locations over here. The second case is when we are running out of time. And so we have this location over here, which is delta alpha, which is the location associated with on the path, associated with the time in which we have 5% of driving time remaining. So we'll start looking for a rest location from this point over here backward. Or we can have the case in which the two situations occurs simultaneously. So we combine the search in this case. The search for the stop location is done differently according to the fact that we are running out of fuel or rest. They are both based on what we call the radius search, which works like this. So in practice, we consider a center point, which is seen in these slides and corresponds to gamma tau in the first case and delta alpha in the second case, which is the point from which we're gonna start. Oh, sorry, this is beta tau in the first case and delta alpha in the second case, which corresponds to the point in which we're gonna start for searching for a stop location. So this is C, our center. We have a radius, which in our case was set to 5 kilometers. And then we have a circle center at the center C. And then we consider all the interesting stop locations that are within this circle, either refueling station or rest locations. So in the first case, when we need to stop for refueling, we start from the location beta tau. We build our circle. We include all the refueling stations that are within the circle. And then we move the center forward for a given distance I. And we rebuild the circle and consider all the refueling stations and so on, up to the point in which we reach location gamma tau, which is when our tank level is 5% of the maximum. And then all the refueling stations that are within these circles are considered as potential stop locations. Instead, when we have to stop for making a rest, we start from the delta alpha location, that is when we have 5% of the driving time remaining. We build our circle. And if there is no rest location in the circle, we go back to it for the distance I. We repeat the search up to the point in which there is at least one circle containing a potential rest location. Why there is this difference in looking for stop locations for the two different cases? Because when we look for a refueling station, we want to diversify the fuel stations that we are considering, because the fuel price there can be different according to the station in which we stop. Instead, when we have to stop for resting, there is no price associated with the station in which we will stop. So we are just interested in finding a place where to stop. So there is no need of having these high number of possibilities of rest locations to consider in this second case. And once we have determined all the stop location, we discard the dominating ones. In case of refueling locations, refueling station is dominated by another one if the fuel price is higher and the detour that we have to go to reach this refueling station is higher too. Instead, for rest location, we just consider once we have found the potential rest location, we just consider the one that determines the shortest detour. Because again, there is no price associated with these rest locations, and it's just the time that it is taken to reach this rest location that matters. And finally, the final thing that we considered, which was also of interest to the company, so the company was asking us to make this additional tool, is the possibility of combining stops. So, for example, if a driver is stopping for making refueling, it might consider the opportunity of combining this refueling stop with a break. So the 45 minutes break, so that when he restarts driving, he has the maximum 4.5, all the 4.5 hours of continuous driving remaining. So we were considering the opportunity of combining a stop for refueling with a stop for making a break of 45 minutes or a daily rest, or a weekly rest. What does it mean in terms of our tree of all partial paths that we were building? It means that each time we stop at a refueling station, we build 4 different partial paths in which the 4 different types of stops are considered. And something similar happens when we are stopping for the break. Instead of considering just we have to stop for the break, instead of considering just stopping for the break, we might consider also the opportunity of stopping for a daily or a weekly rest. And so also in this case, for each rest location, we build 3 different partial paths according to the kind of rest or break that we do in the rest location that we have just determined. Okay, so and this is our overall algorithm, and now I will move to the test simulations and results. So we tested our algorithm on instances that we created on real data. So we consider 3 base instances that differentiate according to the distance they cover. We have a relatively short, medium, and high distance instance. The short one is more or less 500 kilometers long. It is from Fribourg to Maastricht. Then the second is 1,000 kilometers, roughly 1,000 kilometers long from Paris to Brescia. And the long distance instance is from Montreux to Timisoara. For each of these 3 distances, we created different instances according to the initial status of the remaining driving hours and tech level at the origin. So according to the remaining driving hours, we consider the case in which the driver has just had a break before starting from the origin, or just had a daily rest, or just had a weekly rest starting from the origin. And according to the 3 cases, there are, let's say, more flexibility in terms of the remaining hours that can be driven by the driver in the following days. And in the study, according to the initial level of the tank, we consider the 5 cases. The tank is 10, 25, 50, 75, and 100% full when starting from the origin. The fuel consumption is 3.5 kilometers per liter. So this is the standard consumption for trucks. And so in total, we had 45 instances. And we compare our algorithm with the current practice. So we had discussion with the companies and the companies had discussion also with their clients to understand what typically the carriers do when building, when planning their path. And so, according to this discussion, we devised this policy. We tried to mix what carriers do in practice. So, this current practice algorithm works as follows: drivers are assumed not to consider alternative paths, so they just consider the path that is given by the standard navigator. And they also look for a fuel location shortly before running out of fuel. So, I mean, these restrict the possibilities in terms of path that you are considering and in terms of potential fuel location. Okay. These slides over here present the results of the short distance instance. Well, a subset of the just a subset of the instances that we consider. They are quite representative of all the others. So here we have the instance in which the distance is 500 kilometers, and the driver started with just making a break at the origin. For example, here the highlighted lines are the solution of the current practice algorithm and the 2 non-dominated solutions or path determined by our algorithm for the case in which the fuel level is 10% full at the origin. So you see the current practice algorithm drives a path which is 516.5 kilometers long, and the fuel cost is 207 euros, and the duration is 16.42. And it makes a break for refueling and a break for a daily rest. Instead, our algorithm finds two paths. Both of them have a shorter duration or a shorter distance with respect to the current practice solution, and a smaller fuel cost. The difference between the two is that one is slightly more expensive, the first, but it lasts, let's say, kind of 20 minutes less. This different duration is due to the fact that this path number one combines the refueling and the daily rest stop in a single stop. Instead, the second one makes refueling and afterwards, or before that, it makes the daily rest. So we see that in this case, this was not the case for all the instances, but in this for this specific instance, both the paths that are found by our algorithm dominate the current practice. Also, another advantage of our algorithm is that it provides multiple solutions. For example, you see in the second instance over here, when the fuel level is 25%, our algorithm finds 5 non-dominated paths. So this is another advantage of our framework that provides a multiple choice to the customer, and this is definitely an advantage. This table presents the same results, but now in terms of saving with respect to the current practice. And we see that we can have savings in terms of fuel of up to almost 20%, sorry, 30%. And in terms of time, up to 4.5% with respect to the current practice solution. These are the results for the 1,000 kilometer instance. And then you see that we have similar results with respect to the former case. So I will not spend time on that because I would like to leave some minutes also for the questions. But just when looking at the savings with respect to the current practice, we see that on the 1,000 instance, the savings are much fewer with respect to the 500 kilometer instance, but still they are quite substantial, especially in terms of fuel cost. And something similar happens for the 1,500 kilometers instance. The situation is very similar with respect to the two former cases. I'm just highlighting the instance over here when the fuel level is 25% to show you that in this case, we were capable of finding a non-dominated path, and I will show some of them in a couple of slides. Same figure as before, still we can save up to almost 18% in terms of fuel cost, and around 3.5% in terms of time. Okay, and this is what I was showing you before. This is the slide representing the Pareto frontier for the 8 path found by our algorithm for the instance with fuel level equal to 25%. And this is the path from the common practice, which is dominated by these 5 paths from our algorithm, but it is not dominated by the remaining 2. And this is representation of the, let's say, the fastest path from our algorithm, which lasts 37 hours and 30 minutes. Instead, at the bottom, you have the cheapest path, which lasts, let's say, 30 minutes more than the fastest one, but it's much, much cheaper. And finally, on the right, you have the path from the current practice. Okay. So I'm concluding. Well, I presented the possibility our algorithm in which we try to exploit the new technologies in order to provide something useful for the problem that we devised. Just to mention that this software is now currently implemented in the tool that the company is selling to his customers. Thank you for your attention. I will just give this slide here to make a little bit of advertising of the DMAX implementation challenge I'm involved in. And thank you. Thank you for your attention. Thanks so much.